Okay, welcome back. So let me just give you the answers to the two questions that I had asked earlier. Again, you'll be scanning in your notes to send to me, and in those notes, please do include your calculations and your work for arriving at these answers, but this will allow you to check your work. If you calculate A in the example above for the density function of Ian's naps, you'll find that A should be equal to 3/4. Okay, and the other calculation I asked you to do was find the probability that Ian's naps last at least 2 hours, if any given nap will last that long. And that probability is, according to this density chart, should be 1/2. So also please show your work for that question. Whoops, I apologize. That was a mistake that I had just accidentally recorded there. Thanks to Natalie for pointing this out. In fact, A should be equal to 4/3, not 3/4. So thanks for pointing that out. The probability Ian naps at least 2 hours is still 1/2. Okay, so moving on, just let me give you one more example of a probability density function that you'll run into very often. And that is a normal density function. So that's what you sometimes hear referred to as a bell curve. And of course, looks like a bell. So let me go ahead and try to sketch out what a normal density function looks like. Something like this. Okay, and I don't have room to write below the line, so I'm going to go ahead and write it above the line. It has some center point, and then you can actually see here that on either side of the center, there's a point of inflection where the graph goes from being concave up to being, so the graph is concave up here, and it's concave down in the middle, and then again on the side here, it's concave up again. Okay, so the formula for a normal distribution is P of x equals, and it's a formula that involves an exponential, and so it's going to be 1 over sigma times the square root of 2 pi, where sigma is any positive number, and mu is any real number. Okay, and so this is just some constant times e to the, and now there's going to be an exponent here, and the exponent is negative, x minus mu squared. All right, let me make this a little bigger so we can see, and I'm going to go ahead and erase that so that I can make this a little more legible. X minus mu squared over 2 sigma squared. Okay, so this is the formula for a bell curve, and many quantities in nature are distributed according to normal densities. And I guess the one comment I'll make here before we move on is that in fact this curve extends infinitely far in both directions. So if we want to find out the probability, okay, so it is symmetric, right? So the probability that we would be above the mean is 50%, because that's 50% of the area is to the right of the mean and 50% is to the left. But if we wanted to find a more complicated area, we would really need to compute an integral, and often we're interested in looking at integrals that extend infinitely far in one direction or another. So that is some additional motivation for considering what we'll be discussing in this section, general improper integrals. So just to give you a quick definition of what an improper integral is, it is a definite integral in which one limit of integration is infinite. So case 1, or the integrand is unbounded. Okay, and here I'll just comment for this second type of improper integral, the thing to look for are asymptotes. Let me actually just make that more precise. Look for vertical asymptotes. Okay, so let me just give you a couple cartoons. I think that these are useful in kind of being able to recognize graphically when you might be interested in an improper integral. And so a couple examples we've seen include the density function from the preview activity. And in that case, right, if we had some particular time t naught and we wanted to know the area to the right of t naught, then that would correspond to an an improper integral. Okay. Another situation where these arise, as I just pointed out, if we are thinking about a bell curve, right? And this is mu. I didn't mention earlier, so the quantity mu is always in the middle. This sigma parameter up here is the standard deviation of the bell curve, and in fact, sigma is exactly the distance from the mean at which you end up with this point of inflection up here. So you have mu plus sigma and mu minus sigma are these 2 points. Okay, so then we also have this normal density function. There are many calculations we might want to do at which we would want to end up calculating an area perhaps that extends infinitely far in one direction. Okay, and a third situation, let me just give you the cartoon for a third situation here. And the third situation, perhaps we have a function that has a vertical asymptote somewhere. And so maybe in this particular case, if we wanted to find the area that I'm shading here right now, this would also correspond to an improper integral. And the general question that we want to be asking is, so graphically, I've told you what our improper integral represents. It represents that area. And so our question here is, how can we make sense of this idea? So our question is, what is the area? And we'll be defining this in the next short video using limits. So that'll be the topic of what's coming up. For now, though, what I'd like you to be able to do is to recognize the different kinds of improper integrals. So maybe what I'll do is I'll just point out we have infinite limits of integration. Let's just call this star, and then let's call double star where we have an unbounded integral. So in these first two cases that I pictured here, those are where we have infinite limits of integration. This last case here is an unbounded integrand. So what I'd like you to do is, before we proceed to the next video where we actually define and calculate these using limits, what I'd like you to do is go through these 7 examples here and decide which kind of impropriety is present in each, and it may be that there are more than one type of impropriety. So go ahead and do that, and when we pick up with the next video, we will very quickly review those responses and move on to the limit definition that we can use to make sense of the areas that that we're thinking about here.